Welcome. I am going to talk to you about a particular model for understanding the thermodynamics of alloy systems. This is known as the regular solution model. All of you might know that nickel, for example, aluminum, for example, copper, for example, silver, for example, these are metals which crystallize in the cubic crystal structure, specifically the face centered cubic crystal structure. Things like zinc, for example, crystallize in the hexagonal close packed crystal structure. Now, if you take these two crystals, for example, if you take nickel and copper, and if you try to put them together, they actually form a solid solution. This was not known about 100 years ago. For example, people thought that when you take these two materials and put them together, the nickel crystals and the copper crystals are at very small level, and they form, they used to think what is known as a mixed crystals. About 100 years ago, or slightly more than 100 years ago, people understood that more complicated things can happen if you try to put these different types of atoms together. And there is a wide variety of things that you would see when you put them together. For example, nickel and copper forms what is known as an isomorphous system. So, it is completely miscible both in the solid state and in the liquid state, and things like copper and silver, for example, form what is known as an eutectic system, and things like nickel and aluminum, for example, form lots of ordered structures. We will have a more involved discussion about what this order is all about and why it comes about and how it comes about. And if you take something like aluminum zinc, it phase separates. So, there are a wide variety of things that are possible when you take different atoms and put them together. So, the regular solution model, which we will discuss today, is one of the models to understand what happens when you take different types of atoms and put them together. The basis for this model is the Gibbs free energy. So, if you have constant temperature and constant pressure, then in those systems you can understand the equilibrium as one which minimizes the Gibbs free energy. We know that the Gibbs free energy is written as follows. The Gibbs free energy is nothing but the enthalpy minus temperature times the entropy. And in condensed systems, that is solids and liquids, it is a good approximation that the enthalpy is approximately the same as the internal energy. In other words, the term which is added, the PV term, which we neglect. Okay. We will do a short tutorial as to why neglecting this is justified, but we assume so. The G is approximately equal to U minus Ts. Okay, so, this is the beginning. So, we look at this free energy and we try to understand the behavior of systems in terms of this free energy. We are assuming already that pressure is a constant. We are also thinking about systems most of the times which are at normal atmospheric pressure. In such systems, then suppose you have a system which consists of two different type of atoms, say. Okay, one let us call them generically as A type of atoms and B type of atoms. Okay. One of the simplest models that you can think of is that you put together these A type of atoms and B type of atoms and consider a solid. So, we are considering a binary alloy because it consists of two different types of atoms. One I call as A, the other one I call as B. So, A can stand for nickel, for example, B can stand for copper, for example. Okay. It could be any two different species of atoms, and because it is an alloy which is made up of two different types of atoms, it is a binary alloy. We are considering this alloy at normal atmospheric pressure, and when we put these atoms together, then what happens is the question that we are trying to understand. And to do this, to understand what happens when you put them together, we build models. These are thermodynamic models, and the most basic thermodynamic model that we build is known as the ideal solution. In the case of ideal solution, first we define what is known as the free energy of mixing. So, what is free energy of mixing? So, let me again draw a cartoon to explain what this is. Suppose you have some A type of atoms. So, let me represent A type of atoms by open circles. So, these are the A type of atoms. So, this can be standing for nickel, for example, and then you have the B type of atoms. So, let them be represented by filled circles. So, these are B type of atoms, okay. And so, there is a free energy associated with these A type of atoms and with these B type of atoms, and suppose if I take them together, and now I need more number of lattice points. So, there are 4, so I at least need 8 lattice points. And on these 8 lattice points, I try to put these A and B type of atoms, right. So, I try to put, maybe this is a B atom, maybe this is another B atom, maybe there is A atom, maybe another B atom here, A atom here, B atom here, and A atom here. Okay, so, I have now taken the same number of lattice points and I have put them together. So, let us say that this has some free energy. Okay. Now, the difference between this free energy and the free energy of these two is what is known as the free energy of mixing. Okay. So, it is called delta G mix. Obviously, because G is U minus T s, this is equal to delta U minus T delta S. So, if we can calculate this delta U and this delta S, then we can estimate how much is the delta G mix, and the idea is, because systems try to optimize the Gibbs free energy, if this delta G mix is negative, in other words, by doing something, right, it can so happen that if the system is such that suppose when you have these 8 sides, okay, it is preferable to have all be like this, all A like this. It is possible that the system can prefer like this, or it is also possible that the system would prefer to have alternate A and B, right. You will start with A, you will have a B, you will have another A, you will have a B, and here you will have a B, you will have an A, you will have a B, you will have an A, and so on. So, there are several different ways in which this mixing can happen at the atomistic level, and depending on whichever is the one which is going to give the maximum reduction in free energy, whichever one which gives you the delta G mix to be negative and as large negative as possible, that is the one that would be preferred out of this. Okay. So, for the simplest of the approximations, let us do that. This is known as the ideal solution. In the case of ideal solution, okay, we know that delta G mix is equal to delta U minus T delta S. This is mix, this is mix. We assume that this quantity delta U mix is equal to 0. Okay. So, we will later explain why for an ideal solution this delta U mix is 0. So, for now let us assume that it is not there, and now we also want to know what is the change in entropy. So, that can be multiplied with the absolute temperature in which the system is kept, and then we will know how much is the free energy of mixing. We make an assumption in majority of the cases that we will discuss for these kind of alloy models, that the only contribution to the entropy comes from the configurational entropy. In other words, like we were discussing in the earlier slide, whenever you are distributing the A and B atoms on the lattice, you are generating different configurations. For example, you had a configuration at which they were randomly distributed, you had another configuration in which all A was on one side, all B was another side, you had another configuration where A and B were alternating. So, the entropy associated with these different configurations is known as configurational entropy, and most of the times, majority of the times, we will concentrate only on the configurational entropy differences. So, the delta S mix becomes nothing but the delta S mix of configurational entropy. Okay. So, what is this configurational entropy? How do we calculate it is then the next question. So, we are considering a binary alloy which consists of A and B type of atoms, and by definition we know that entropy is nothing but k logarithm of omega, where omega is the number of microstates as they are called. Okay. In the case of configurational entropy, omega is nothing but the number of ways in which you can distribute. Suppose you had Na number of A atoms and Nb number of B atoms, and you are trying to distribute them on n number of sites. Obviously, n is equal to Na plus Nb, if you assume that this is a binary alloy and there are no defects like vacancies. Okay. So, you have n number of sites which is equal to Na plus Nb, and where Na and Nb are the number of A and B atoms respectively. So, you are trying to distribute Na number of A atoms and Nb number of B atoms on n number of sites, then the total number of configurations that you can generate, if you assume that you cannot distinguish A and B type of atoms, happens to be n factorial divided by Na factorial Nb factorial. Okay. Now, why is the number of configurations given by n factorial by Na factorial by Nb factorial? Let us try to do a little bit of algebra. Okay. So, let me say that I have 4 distinct atoms. Okay. Let us call them as 1, 2, 3 and 4, and let me say that I have 4 sites. Okay. Let me also label these sites as say A, B, C and D. Okay. So, the total number of ways in which I can put this 1, 2, 3, 4 on A, B, C, D is as follows. For example, for A, I can choose 1, or I can choose 2, or I can choose 3, or I can choose 4. Once I have chosen 1 for the A site, for the B site, either I can choose 2, or I can choose 3, or I can choose 4. If suppose I have chosen 1 for A and 2 for B, then C and D, there are 2 possibilities. So, one is where I choose this to be 3 and the other one is 4, the other one where I choose this to be 4, the other one is 3. So, in other words, it happens to be 4 of these choices for the first one, and then there are 3 choices for each one, because when I have 2, for example, I can have the choice 1, 3 and 4. So, for each one of these, then I have 3 choices, and each one of these then I have 2 choices, and once I have exhausted, for example, 2, 1, 3, if I have chosen, this has to be necessarily 4. So, there is only one choice. In other words, this is equal to 4 factorial. That is, if I have 4 distinct atoms and if I have 4 distinct sites, if I can distinguish between those atoms, that is nothing but 4 factorial. If I have 4 atoms, it is 4 factorial. So, if I want to distribute it on 4 sites. Suppose if I cannot distinguish 1, 2, 3, 4, they all are identical, that I can only name them as, say, for example, A. Then I do not know which is 1, which is 2, which is 3, which is 4. That means, then I have to, that there is only one way, because all A and you have 4 sites, you will just put A atom on also. So, 4 factorial by 4 factorial. So, if suppose you have, say, let us say you had some 16 sites. Okay. So, you will have 16 factorial ways, provided they are all distinct entities, but if suppose out of which some m of them are indistinguishable and some n of them are indistinguishable, which give together this is equal to 16 say, then the number of ways in which you can distribute is 16 factorial by m factorial by n factorial. Okay. Oh, if you have this m plus n, m among themselves indistinguishable, n among themselves indistinguishable, you can think of it as total number of balls, for example, is 16, m can stand for red balls and n can stand for black balls. So, you have say some 7 red balls and 9 black balls. So, what is the total number of ways in which you can arrange them, the total number of different configurations you can have, where you are not going to be able to distinguish the red balls among themselves and the black balls among themselves is this. So, we will again do a small tutorial to understand where this division by m factorial n factorial comes, but you can see, for example, if they are all the same, then it will be 16 factorial divided, because there is only one way in which you can arrange. Okay. Now, we consider, given this information, we consider the following case. What do we consider? We say that I have total number of sites as n, and I have n a atoms of A and n b atoms of B, and the total number of sites is nothing but n a plus n b, and initially the initial configurational entropy, because I had only A atoms and n a sites. So, there is only one way, logarithm of 1 is 0. So, the initial configurational entropy is 0. Similarly, the initial configurational entropy for all B atoms is also 0. But the moment I put them together on a lattice, I get this number of configurations that is possible as n factorial divided by n a factorial n b factorial. Okay. Because the initial configuration gives 0, so the delta S mixing of the configurational entropy is nothing but this itself, which is k ln omega. Okay, because the other quantity, the omega is 1, so ln 1 is 0. So, there is some minus of k ln 1 kind of terms. Okay, another minus k ln 1. One is for A type of atoms, another one for B type of atoms, this is all 0. So, this is all we have as the delta S mix of configurational entropy. Now, let us do the algebra in a little bit more of detail. So, this is the configurational entropy. I have delta S mix of configurational entropy, that is nothing but k logarithm of n factorial divided by n a factorial n b factorial. Now, we use an approximation called Stirling's approximation. Stirling's approximation says logarithm of n factorial is n logarithm of n minus n. Okay. This is a very good approximation for large n. In fact, we will do another tutorial to find out for what value of n this approximation is good. Okay. But for now, let us say that this approximation is good. Remember, if you take 1 mole, for example, this n is really a large number. It is like a number of the order of 10 power 23. So, Stirling approximation is very good for such large numbers. But for now, let us assume that this approximation is okay. So, then you can calculate the delta S mix configuration, which is nothing but k, right. So, log something by something. So, it becomes log n factorial minus log n a factorial minus log n b factorial. Now, if we do, then it becomes k by this approximation n ln n minus n. There is a minus sign. So, it becomes n a ln n a minus n a plus, because there is a minus sign, and similarly it becomes n b log NB plus NB. But remember, n is nothing but Na plus Nb. So, minus n, Na, Nb will go away. So, we are left with n log n minus Na log Na minus Nb log Nb. Okay. And you have n, let me write that n as Na plus Nb log n minus Na log Na minus Nb log Nb. This is what we have. So, let us expand and do a little bit of algebra. So, what do we get? We get delta S mix configurational is nothing but minus k Na log n, sorry, minus is pulled. So, this is minus Na. So, minus Nb log n plus Na log Na plus Nb log Nb. So, this is what we have. Now, let me also, okay, so minus k, let us do the, so Na you can take as common. So, it is log Na minus log n. So, that becomes Na log Na by n plus Nb similar fashion log Nb by n, right, because Nb you can pull out, it is log Nb minus log n. So, that is nothing but log Nb by n. So, Na by n, let us call it as, so these are the atomic fraction. So, number of A atoms to the total number of sites, number of B atoms to the total number of sites. So, let us call Xa as Na by n and Xb as Nb by n. Because Na plus Nb is equal to n, Xb is nothing but 1 minus Xa. Okay. So, this is because, why is this? This is because Na plus Nb is equal to n. So, if Na by n is Xa, then Nb by n will be 1 minus Xa, because we are dividing on n on both sides. Okay. So, this becomes, so we have delta S mix configurational as minus k. Let me also multiply by n here and divide by n here. So, I have Na by n logarithm of Xa plus Nb by n logarithm of Xb. But again Na by n is Xa. So, we get the expression minus k n Xa log Xa plus Xb log Xb. So, this is the configurational entropy. So, you can now calculate the configurational, the free energy of mixing, because we said that for the ideal solution there is no contribution from the internal energy of mixing or enthalpy of mixing. In the case of condensed systems like solids and liquids, these two are assumed to be the same, and it is a very good approximation. So, we have delta G mix, which is the free energy of mixing, as nothing but minus T delta S mix, and we assume that this delta S mix is only the configurational entropy. There could be vibrational entropy contributions, for example, which we are not considering, which means you have minus T times K n times Xa ln Xa plus Xb ln Xb. Remember, there was a negative sign, so this becomes plus. If you assume that this n is the Avogadro number, K is the Boltzmann constant times Avogadro number. So, if you consider this quantity as n as 1 mole, right. So, then you have T times R, which is the universal gas constant, times x A log x A plus x B log x B. Okay. So, this is a positive quantity, this is a positive quantity, logarithm of some fraction. So, this is going to be a negative number. So, delta G mix is less than 0. In other words, ideal solution, this is called ideal solution because the configurational entropy is always going to reduce the overall free energy. So, if you take a system in which you have all these A atoms and you have these B atoms, and if you try to put them together in the absence of enthalpy of mixing, okay, or internal energy of mixing, then it is always favorable for the system at any temperature above 0 to have mixing, because mixing then reduces the overall free energy. That is the reason why it is called ideal solution, because it will always mix very homogeneously, because the perfect mixing, randomly arranging the A and B atoms on the given lattice, which is what we have assumed when we are deriving this, is the one that is also going to have the lowest free energy. So, the system is going to choose it in such a way that it is going to randomly arrange these A and B atoms. It is also ideal solution in another sense, in the sense that it is not, you are thinking that you are putting A atoms and B atoms. As far as the system is concerned, it is not showing any enthalpy change or internal energy change. That means, it is not distinguishing between A atoms and B atoms. In that sense also it is an ideal solution, because it is not distinguishing between A type of bonds, A B type of bond, B B type of bonds, it is treating all of them to be equal. That is the reason why the enthalpy of mixing or the internal energy of mixing is 0, and that automatically also results from entropy considerations a complete mixing. Okay. So, this is known as an ideal solution. So, ideal solution always gives a free energy of mixing which is negative. So, because the free energy of mixing is negative, ideal solution always have this actual solutionizing effect. It will take the atoms, it will take on a lattice and it will distribute them randomly. Now, let us discuss the next model, which is slightly more complicated than the ideal solution model that we have discussed till now, but we are going to introduce some approximations which can sometimes be questionable. So, I am going to tell you what those approximations are, and I am also going to show you how the expression is derived. In the case of what is known as a regular solution model, okay, we assume that in delta G mix, remember you had two terms, one was delta H mix minus T delta S mix. We are going to assume that this delta S mix is still given only by the configurational entropy, and what is more, the expression that we derived by assuming that the A and B atoms are randomly distributed on the given number of lattice sites, we assume that that approximation is also valid, and we use the same expression that we derived in the ideal solution case, namely that this is nothing but R times x A log x A plus x B log x B with a minus. This is what we are going to assume for the configurational entropy. In addition, we are going to assume that this delta H mix, which was assumed to be 0 in the ideal solution case, is not equal to 0. That is what makes it this regular solution model. That, and we are also going to assume that even though the delta mix x delta H mix is not equal to 0, it is still a small number. Okay, delta H mix is still a small number. Why is this important? You will see that the delta H mix is related to the differences in bond energies between AA, BB and AB kind of bonds. So, if you assume that this delta H mix is a considerable number, then this assumption that we are using when we are writing this configurational entropy is not quite correct. Okay. If suppose the system for example prefers AABB bonds or AB bonds, then a random distribution of A and B atoms on the given lattice is not going to happen. So, this configurational entropy calculation then becomes not quite correct. To make sure that this is still valid, we are saying that okay, this delta H mix is not 0, but it is still not very considerable quantity. So, at higher temperatures this will still dominate, and at very low temperatures where this term is not so dominant, this will dominate. So, if you can find systems where such a neat distinction exists between at low temperatures where it is mostly controlled by the delta H mix, and at high temperatures it is mostly controlled by delta S mix, then for those systems this model called regular solution model works really nicely. So, in the regular solution model we assume that delta H mix is not equal to 0. On top of it we actually assume that this delta H mix is equal to some omega, this is known as the regular solution parameter, times XA times XB. Remember, because XA is 1 minus XB, it is also 1 minus XB times XB. Okay, so, it is a kind of parabolic relation. Omega is known as the regular solution parameter, and omega we will do another tutorial to show that this indeed is so, is nothing but the Avogadro number times Z, which is the number of nearest neighbors in the crystal structure that you are assuming, times a quantity called epsilon, and epsilon is nothing but the difference in the bond energy. Okay, so, epsilon is nothing but EAB minus half of EAA plus EBB. In other words, epsilon is a quantity which tells, suppose if I take two AA and BB bonds, break them, make AB bonds, what is the difference in energy. Okay. So, omega, which is nothing but the others are either geometric factors or numbers. Okay. So, total number of sites that you have, the number of nearest neighbors in the crystal structure that you are assuming, which is for example 12 if it is FCC, 8 if it is BCC, and so on, 6 if it is simple cubic, and so on. So, this omega, basically the sign of omega depends only on this quantity, because like we said this is nothing but Z times epsilon. So, epsilon is positive, that means AB bonds have higher energy than AABB bonds. Epsilon is negative, which means this EAB is less than this quantity, that is AABB. Okay. So, this omega picks up the sign according to what the sign of epsilon is going to be. So, the delta H mix, which you can see, is dependent on omega XA into 1 minus XA. Again, so the delta H mix sign is dependent on the sign of omega. So, in this case, now the free energy delta G mix, okay, which is given by delta H mix, okay, minus of the T times delta S mix, but delta S mix is nothing but minus R times XA ln XA, XB ln XB. So, let us write down the full expression, it is omega XA into 1 minus XA plus RT times this multiplies XA ln XA plus 1 minus XA ln 1 minus XA. So, in this case now the sign of delta G mix, so this quantity like we discussed earlier is always negative, because logarithm of a fraction, logarithm of fraction. So, this is going to be less than 1. So, this quantity is always going to be negative, okay, and it is also parabolic. Okay. Now, this quantity, if suppose this is negative, then everything is negative. So, there is no problem, but if suppose this quantity is positive, then this can swamp this quantity sometimes, and that leads to interesting microstructures. But in all cases, suppose if the temperature is very high, then this omega parameter, because we have also assumed it to be very small, because we assumed that this epsilon that makes part of this omega is very small. So, this quantity is negligible. So, at higher temperatures the system is still driven by the entropy contribution. Only at lower temperatures, depending on the sign of omega, whether it is positive or negative, then either it is going to go the same way as the entropy or it is going to go against entropy. In either case, it is going to have important effects. To understand this, let us assume that we are at absolute 0, then the T is 0. So, there is no configurational entropy at all, entropy contribution is completely not there, in which case the system's behavior is completely determined by the regular solution parameter. And what does the regular solution parameter say? It says that it depends on whether, suppose if you take AA bonds, BB bonds, you break them and you make AB bonds, and making those AB bonds is going to be costlier, right, in which case the system would prefer to have AA and BB bonds. That is, the system will phase separate. The system will get a configuration like I showed you earlier time, in which it will have all A atoms here, all B atoms here. Please notice, even if it does that, it still has to make some AB bonds which are costly, okay, which are relatively costly. If possible, it would like to have all A bonds and all BB bonds. On the other hand, suppose making AA and BB bonds is costlier, and if it breaks them and if it makes AB bonds, on the average if AB bonds are cheaper, that is when it is going to make the other configuration that I tried to show you. What is that configuration? It will try to have only AB bonds, right, it will try to have only AB bonds. So, you can see AB, 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 right, AB, AB. So, this kind of mixing that happens at the atomic level leads to what is known as ordered crystal structures. We will look at more details, and this is known as ordering system. This kind of separation is known as either immiscible, right, because they are not mixing, or phase separated, right, because the two phases are separated. So, in other words, and in either case, if this is true only at absolute 0, at any temperature above absolute 0, the entropy is always trying to make the system go to a more random configuration. It neither prefers this nor prefers this. This is too ordered, this is also too ordered from the entropy point of view. Entropy would like to mix them as randomly as possible. And all systems at higher temperatures, where entropy contribution becomes the dominant factor, will anyway go through this more mixed, completely solution kind of structures. Okay. Only at low temperatures, depending on the sign of epsilon and in turn which decides the sign of omega. So, the sign of omega decides whether the system is going to phase separate or the system is going to order. The models that we are going to talk about in this course, which is known as phase field models, are basically models meant to study this kind of phase separation by a specific mechanism known as spinodal decomposition and ordering. Basically, all phase field models can be thought of as models built from these two basic components. Model one, which is known as Cahn-Hilliard model, which was written to explain this phase separation behavior through a specific mechanism, and another model which is known as Allen-Kahn model, which was written to describe this ordering behavior. And all phase field models, at least as far as this course is concerned, can be thought of as combinations of these kind of Cahn-Hilliard like and Allen-Kahn like models. So, that is the reason why we are starting from this regular solution model, and we are trying to see. So, remember, regular solution model is a thermodynamic model. It is talking about the free energies. From free energies, it is trying to predict at equilibrium what is going to be the structure of the material in question, whether it is going to form an uniform solid solution where all the atoms will be randomly distributed, or it is going to form an ordered crystal structure where over and above the crystalline order you will have specific occupancy preferences for specific type of atoms. Like if I have nickel, for example, I would like to have only surrounding aluminum atoms, no nickel should be next to another nickel. If I have aluminum atoms, I should have only nickel surrounding it, no aluminum should be next to it. So, this kind of ordered structures, or if I have some aluminum zinc kind of system where I have aluminum rich regions and zinc rich regions. So, this is the kind of problems which are tackled using the phase field models, and so it is always a good starting point to understand phase field models, to start from solution models. So, what we have discussed today is two different types of solution models. One is known as the ideal solution model, the other one is known as the regular solution model. In the ideal solution model, we said that delta H mix is 0. So, the configurational entropy, which is the only contributing factor we have assumed in this kind of binary alloys, then shows that the system will always have random occupancy for A and B atom. So, in that sense it is an ideal solution. Okay. So, it is going to be having a very complete mixing. Okay. But it is also ideal in the other sense of the word, namely that delta H mix, which we assume to be 0, is nothing but a representation of the cost associated with making an AB bond by making AABB bonds. So, when we are assuming it to be 0, we are saying that on the average breaking an AA bond and breaking an AB bond and making two AB bonds is going to be the same in terms of energy cost associated with this process, which means the system, in other words, is not distinguishing between A and B type of atoms. So, in that sense also it is an ideal solution, because it is not distinguishing between the different atoms, it considers them almost like the same species of atoms and it distributes them randomly on the given lattice. So, that is the ideal solution. Of course, that is a very ideal case, which means it never really happens practically. And for the other case, where we look at a slightly improved version, which is known as the regular solution model, it still is bad in terms of some of the approximations that it makes. The most important bad approximation that we have made is that we have assumed that the distribution of atoms is still random as far as entropy calculation is considered, but we have also said that the enthalpy of mixing is not 0, which means AABB bonds and AB bonds, there is a preference for one or the other, which means assuming random distribution is really not that correct, but it is okay in some approximate cases where the delta H mix is not 0, but it is also a number which is not too different from 0. Okay. It is a very small number. In such cases, a regular solution approximation is good. So, we are going to use this regular solution model, and at high temperatures anyway all models are going to give you more ideal solution like behavior, because the delta H mix becomes not so dominant, the T delta S mix term becomes dominant, and that will always prefer a random substitutional solid solution. Okay. So, we will start from this point as the starting point for the next module that we will have, in which we will talk about deriving phase diagrams from regular solution like models, and what do they tell us about the kind of phases that can exist in binary alloys. Okay. So, I am going to stop it here, we will discuss it in the next module.